Hello, Borden.
Hello.
Hello, Christian.
Yeah, sure.
Hey, Jeremy.
Hello.
Okay. Okay. That was the homework due today, and I haven't posted the new homework, but this will be homework 9, and it will be due next Monday. We have about 4 weeks remaining, and somehow I'll switch the homework whenever there is a smaller homework, or maybe the next homework will be due on Friday, so that we can have the last homework due on the Friday of the last week of classes. So you can expect 3 more homework, right? 10, 11, 12. Your final exam date is May 3rd. Monday. Okay. So we are in a point where we want to take over or take up this time dependence completely. We have done electrostatics as one regime of electrodynamics, that is another is magnetostatics, and then we also talked about relativity, where it seems like uh, when you move, first of all, speed of light is constant, and when you move things, things look different, especially electric and magnetic field is going to look different. So we want to see how all this gets connected. So let's go back to Maxwell's equation, and first of all, have the complete time in there. And the first thing we have to do is we have a point charge. It has an electric potential, and we would like to generalize that to have time in it. Like, what is the electric potential due to a single point charge when you have time dependence in it? So we want to write down the equations first to learn this. So let's recall our Maxwell's equation, since we did relativity for some time. So for Maxwell's equations are divergence of the electric field, and I'll prefer to write my epsilon naught on the right hand side. That was your charge density, and all the time we were looking here, maybe I should stress on this. So we were having no time dependence, so keeping some room there. There was no time dependence, right? But now we want to actually introduce time dependence, or we want to not neglect this time dependence. So that's a new thing. And how does elementary point is, how does electric potential due to a point charge, which we will call the Green's function. The divergence due to magnetic field does not change earlier or later, so at least this equation doesn't change. Even with the time dependence, the Gauss's law also did not change. What does change is that the curl of the electric field in time independent situations or static situations is equal to 0, but now it's no more 0. So the moment you introduce time dependence, you can talk about change in the magnetic field, and change in the magnetic field can create a curl in the electric field. That's the idea, and that's Faraday's law. In introductory physics courses, we come across situations where this really contributes at a macroscopic level. The fourth equation is P r comma t is equal to time derivative of epsilon naught times electric field plus actually, since I've written it in terms of mu, I should also say this is epsilon naught mu naught dt of the electric field plus mu naught times j, and this is r of t. Let's keep, we do realize that charge density acts like a source, current density acts like a source. So let's keep that on the right hand side. Doesn't matter much, but just clarifies the point that that's actually the source, and let's write our equations in this form. So just move the equal sign to the All right. I would like to get an equation. Remember that earlier we have seen that it is convenient to write everything in terms of scalar potential and vector potential. So we will keep that same strategy. And now we would like to have the complete situation. And just the fact that the divergence of B is 0 implies that this implies that B can be written as curl of a vector potential. So that is a vector potential. And the moment you have a vector potential or magnetic field can be written as a curl of A, substituted in the second equation, that is a total curl, which means that if we together put this in, so we have curl of the electric field plus the time derivative of A, right? So plus the time derivative, a partial derivative of the vector potential is equal to 0, which reads that the curl of something is equal to 0. The moment you say curl of something is equal to 0, that means that quantity can be written as a gradient of that quantity. So this implies immediately that electric field is equal to negative gradient phi, and you take the time derivative of the vector potential to the right hand side. And that's our, so we want to write all our Maxwell's equation in terms of electric potential and vector potential, and that's our conversion factor, if you want. So let's substitute this in the first equation there. That will give us one relation, and we will get the second relation by putting this in the fourth relation. Right? Let's begin by substituting this in the fourth equation. And what we have is okay. So we have curl of magnetic field, which is nothing but curl of A. That's minus of, that is an epsilon naught mu naught. That's epsilon naught mu naught, which is basically 1 over c squared there. But let's delay that substitution. And derivative of the electric field, which is negative gradient of phi minus dA by dt. That's equal to mu naught times J. We have done this before in the magnetic case, except that there was no time derivative there. So pretty much the same idea here. This will be equal to the gradient of the divergence of the vector potential minus the Laplacian of the vector potential. And notice here there is a plus double derivative of A showing up, the plus sign. And that's epsilon naught mu naught and we also have this piece here which reads epsilon naught mu naught time derivative of gradient of the scalar potential. That's all equal to mu naught times J. Recall that epsilon naught mu naught is equal to 1 over c squared. And let me rewrite this in the form so that it's as close to the static equation. It's your vector potential A, and let me write it as a function of R and T here to emphasize that there is time dependence in there. Let me remember that in magnetostatics, the divergence of A was chosen to be 0 as a gauge. We said that there is an independence there, and we can actually choose that, but that's not what we want to do at this point. I want to move this whole thing to the right. This is J of RT. And there's two terms remaining. I will write that as divergence of the gradient of divergence of A, that's this piece. And there is one more piece, which is plus 1 over C square d by dt. And what we are going to do is that the gauge that we had, we said we are going to be working in a special gauge that actually is a special case of a more general scenario, and the small quantity is going to be chosen as a gauge. This will be chosen to be 0, and that's our gauge. As far as we stay consistent with this gauge choice, we are allowed to choose the gauge once. It's like choosing the origin. Like we have a constraint on this fields, or there is a freedom in this fields. It's like we can choose our origin wherever we want. We can fix it once. And that will be called the Lorentz gauge. So if we choose that, we have our equation immediately reduces to we call that this is a wave equation. And if you were to ignore the time dependence, then it becomes our a magnetostatic situation. But we want to keep the time. And that's the equation for the vector potential. And the same similar equation comes out for the scalar potential also. Let's see that. So this time we substitute the electric field. We have divergence of gradient of phi minus dA by dt is equal to rho over epsilon naught. But we have a choice. We set our gauge to be divergence of A is the same as time derivative of phi. Use that to substitute it in here. This is minus Laplacian of phi. There's a negative of divergence of A. So that's negative time derivative. Divergence of A is nothing but plus time derivative of phi. So this is plus 1 over C square. It's not, it's multiplied, right? So it's 1 over C square. No, minus, right? Minus. And this is d phi by dt. That's because the gauge choice allows you to replace the divergence of A as minus 1 over C square d phi by dt. So it replaces the divergence of A with respect to d phi by dt, and that's equal to rho or t. So we again get the same equation. Plus 1 over c square. And that will be our equations for the scalar potentials in the non-static situation. Very similar to earlier situation, it's just we have this time dependence showing up, which means it's a wave equation. The scalar potential and the vector potential behaves like or satisfies the wave equation with the charge density and the current density acting like sources. And of course, we have chosen a gauge, which is divergence of A plus the time derivative of the scalar potential is 0. So let me rewrite those two equations in the same one underneath the other and emphasize that. And that's your naught. It is good to write the following in the following manner. I'll put a C in here in the denominator there, which will mean I have to put a C in here also. And then so there is an epsilon naught there, so I'll move that to the right. So that's 1 over epsilon naught. And I put in a C in the denominator there, which means that I have to write an 1 over epsilon naught times mu, right? But C square, how do you do this? Phi naught C, yeah, so I have to put a C there. C here. And C square is mu naught times epsilon naught, so that's the same as mu naught. So so instead of writing phi, what I want to write is phi of r comma t over c, and the right hand side was rho. Instead of that, I write c times rho times r comma t. I've introduced a c square on the right hand side, but there was already an epsilon naught, so that gives me a mu naught. So let me write this as mu naught times c rho of rt. Why did I do that? The idea is that, remember, in relativity, we treat every physical quantity needs a fourth component, correct? Position gets time as its fourth component, momentum gets energy as its fourth component. We had, what else did we introduce? Velocity had speed of light with a gamma factor as its fourth component. So what we are going to see is that the vector potential and the scalar potential with the factor of c satisfies that condition that so the scalar potential with the factor of c will be the fourth component of vector potential, and the charge density will be the fourth component of J. So what we can say is a mu is equal to phi over c times vector A. So that's the point, and J mu will be c times rho and vector J. And it is, how about this? quiz, right? So it's a good idea to check that the dimensions of phi over c is exactly the same as the dimension of A, right? Dimensionally, they should all match. So check, verify that dimension of phi over c is the same as A, and check that dimension of c times rho is the same as the dimension of J. That's why you introduce your J's. Okay. So now that we have got our equations, so we can say negative Laplacian plus time derivative plus 1 over c square time derivative square. In fact, it's the same equation, so it is sometimes also written as phi of RT over C. Or let me go back to our standard form so that you see it more clearly. So this is phi of RT, scalar potential and vector potential. The two equations, just writing it in a single form, is the first equation has a source as epsilon naught, the charge density, and the second equation has a source mu naught times the vector or the current density. It's clear that if you had to have set t equal to 0, or if the time derivative is not there, it goes back to your electrostatic case where the vector scalar potential comes in, and the second equation is the magnetostatic case where the vector potential comes in. All this leads to the idea that if it was statics, we are dealing with the equation negative gradient of something, right, we just call the Green's function, is equal to a point charge, right? If it was a point charge, so that's just a delta function. And it gives you everything. If it was statics, you start with this equation, and this implies the point charge, right? So this implies that G is equal to 1 over 4 pi times 1 over r minus r prime. That was the electric potential due to a point charge, if you want. It was also the magnetic potential due to a moving charge, moving current. Both had the same Green's function, and from there we actually immediately wrote down our phi and A. So what did we do here? Remember, once we recognize this, we just set scalar potential, or at any we don't have time dependence now, so this is equal. Since there is this epsilon naught that multiplies that, that's 1 over 4 pi epsilon naught, and rho over, there is no time dependence, we are talking about statics, and r minus r prime. And this could be anywhere, like for each r prime there is a contribution, so you integrate them. Right? That's superposition. So you use superposition principle to find the scalar potential. This is just a reminder that what we did, once we have the Green's function, we are calling the Green's function basically the electric potential due to a point charge, then we add them up. So this is superposition principle. And the same thing for A, since there was a mu naught in the numerator this time, we said it is mu naught over 4 pi, same piece, right? 1 over r minus r prime, and this time you multiply J of r prime, or time dependence is gone, and then you again superpose them. Superposition principle gives you your total vector potential and your total scalar potential, given a charge density. Like integration is basically adding them all. But what about, so we release the statics, right? So now we are saying that so if it is not static, it will be dynamic. So electrodynamics would be, now we want to talk about what is the solution for this equation. Since both the scalar potential and the vector potential satisfy the same equation, we want to talk about what is this, and more precisely just giving it in detail. So this is r minus r prime and t minus t prime. And this time, the right hand side is not just a delta function in position, that is time also. If you recall, I never actually found the solution of this Green's function for you guys, so you should have done it. It is not that involved, but for keeping time and other things into picture, I just gave you the Green's function. I said that the electric potential due to point charge is that can be derived from the starting from the Maxwell's equation. You can get those things. Same thing we will do here. I will skip the derivation of the solution that I'm going to write. I'll just say that the Green's function does. So we're talking about a point charge. Imagine a point charge at r prime. What will its electric potential be at r prime, or observation point r, if we were to introduce time dependence? That will be equal to, it will look very similar to the old one. In the static case, we had r minus r prime. How does it change? That is a delta function now on in the numerator. And what is the delta function of? And now that we have relativity, we will be able to interpret this, what this means. So this will read t minus t prime. Like read that as a single variable. If you set t prime equal to 0, then that's the time elapsed, right? Time elapsed between 2 points, and t prime should again be thought of as a source point whenever the source emitted something, and minus of the time taken to travel a certain distance. So let's interpret this instead of deriving it. Let me try to give you a feel for what that delta function is meaning. So for simplicity alone, let momentarily, right? We won't keep this permanently. So let r prime be equal to 0 and t prime is equal to 0. We can choose our time to be 0. Actually, don't set r prime equal to 0 because then it will become static, right? So I don't want to permanently keep it like that. So let's just say t prime is equal to 0. So something happens at t prime, and the time begins from there. Then we have g r minus r prime comma t is equal to 1 over 4 pi delta function of t minus, notice r minus r prime is a distance. Especially with that magnitude, it is not a vector relation, it is the distance between 2 points. And what does this mean? So we're talking about the electric potential due to a point charge, right? If there is a delta function, it means that there is a contribution only when this is satisfied. Otherwise, it is zero. Remember your delta function definition. If the argument of the delta function is set to zero, that means there is a contribution. If it is not equal to zero, there is no contribution. Correct. So that means this gets contribution only at one time, at one moment in time. Correct. It's a very special case. So let's see. So let's draw a diagram to give you a feel for what this is. So let's say there is a charge going like this, right? That's an arbitrary curve, and this is a positive charge, and this is a path of a positive charge. So that's your at some time t prime equal to 0. So this is position r prime. That's your vector r prime. That's the position at t equal to t prime. Since the charge is moving, its position will not remain the same once you have evolved in time. Like after the moment you evolve the time, that charge is moved from r prime to the next point, right? So let's say at t prime equal to 0, which is what we have set. As time evolves, so let's say this is our observation point. That's your vector r, that's your origin, so that's your vector r. We are asking what is the electric field or the electric potential at this point, because this charge is sitting at r prime. And it just passed r prime, so we don't, it doesn't stay at r prime for long. It just stayed there for a moment. And when will this know about it? It will not know about it at t prime equal to 0. Instead, it will take some time for this information to go from r prime to r. And how much time does it take? That information goes at the speed of light. So how much time will it take to evolve, go from there to there? So t is equal to the distance divided by speed of light. And the distance is r minus r prime divided by speed of light. So after the charge has crossed this point, wait for a certain amount of time for the speed of light to reach here. And at that instant, it will know, oh, the charge went there. So it gets an information from that. And since the charge has left after that, the very instant the charge has moved on. After that, it doesn't know about it either, at least from this point. After that, the next instant, it will get the information from the next point. From the next point, it will get the information from the next point, and so on. That keeps happening. But from position r prime, it gets a signal only once, and that's what that delta function means. Imagine you're a traveler and you're sending let's say old postal mail every one day, and someone is receiving your mail. If you are traveling towards your home, the frequency will be different. You're going away from the home, the frequency will be different. But if you periodically send your mail, you will surely get the mail at some instant. But from how far you're coming, that's decided by the point itself. So you can imagine that with that analogy, maybe not the perfect analogy, but hopefully this is reasonably clear. So the delta function has that, that's an interpretation of that a delta function. And clearly, this is a statement that signals go at the speed of light. That's the underlying statement. Okay, so what is our electric potential and vector potential, right? That's what we are interested in more. Earlier, remember the first, right, our earlier statement. If there was no time dependence, I'm going to extend this very quickly. So this, I'm going to put in a time there. So first I'm using the static scenario for recalling what we did earlier. So this was d cube r prime. Leave some space here. I'm going to introduce something there. And that is 1 over 4 pi epsilon naught. And there was r minus r prime. And we had charge density. That was how the scalar potential worked. How does it change? Our new potential is having a delta function, t minus t prime minus r prime over speed of light. And we have to integrate over time because we are observing the charge for all times, right? It's just that the signal is retarded. So now introduce the time t. This depends on t prime, and you have to integrate for all time. Here also we are integrating over all space, right? All space and all time. And only at those points where this is satisfied, that means the signal has to start from a certain, from the r prime and reach r, only at those points we get contributions. Otherwise, we do not get contributions. Same thing for the vector potential. It's equal to, I can bring out the mu naught over 4 pi. This is d cube r prime and this is d cube prime minus infinity to or plus infinity and instead of charge density this time, I will have we have a delta function sitting there, and we need to learn to evaluate this delta function. All the time we have used the delta function every instant until now. We have had linear quantities inside that. And for the first time, we are going to see that even for the simplest scenario, unless it is a static case itself, this is going to evolve in time. And when it evolves, this distance is going to change. So let's talk about that, at least construct the problem. We will have to come and work on it in the next class, but let me construct this problem here. So let's say that instead of having a randomly moving charge, so let me say a positive charge is moving uniformly along the z-axis. So this is the z-axis, it's moving, and that's your velocity v. So what's its position? So position is, let me say that's R prime is equal to 0 in the I direction. Let's say it is moving along the Z axis, right? So it's X is 0, Y is 0, and the Z axis, it is moving with uniform velocity V. So if it started from Z equal to 0, as time evolves, it keeps growing. So how much does it go? It depends on the velocity V. There's a time dependence in the position of Z. Since this is the property of the source, so let me say this is T prime. It doesn't matter T or T prime, but when I put it in the integral, I will need the T prime. Of course, its velocity V is the derivative of position here. That's 0I plus 0J plus velocity in the K direction. Right? That's the description of a positive charge moving along the Z-axis with uniform velocity. And what we are interested in is what is its electric field going to be and what is its magnetic field going to be. Since it is a positive charge, we know that it will have an electric field. Even at rest, it has an electric field. But how is it going to change, right? Is just because it is moving, what happens to the electric field? That's the first thing we want to ask. And what is the magnetic field also, right? Since it is moving now, it has a current density associated with it. So what is the magnetic field also? So that's the questions we are interested in asking. So the first thing we have to write down is the charge density, right? So the charge density, this time having a time dependence in it. What's that? Well, it's a point charge, so it's a delta function, correct? So it's a point charge Q, let me say this Q, right? It's point charge with charge Q. Where is it sitting? So it is delta. So that whenever x is 0, so whenever x prime is 0, all through, right? X prime always remains 0. There are 3 delta functions. Y prime always stays 0. What about z prime? The position of this is given by vt prime. So this is z prime is vt prime. That's your charge density. Is that very clear? Any questions? Right. If it was static, you would have suggested that 0. That's the only difference that's happening. Current density J is always just multiply the velocity. This time it's a velocity vector. So V prime. So it is V prime. Right? This vector, which is basically just V times K, multiply it with rho, right? So that's how we get your charge density for a point charge all the time. You multiply the velocity with the charge density, you get current density, which is more explicitly equal to Q times V prime, which is basically just having one component, Q times V times K, K hat, you want, times delta of X prime, delta of Y prime, and delta of Z prime minus VT prime. Again, the only difference is this piece here, right? This piece in there. But remember that we also have our Green's function different, or the electric potential has an additional delta function in there. So in the last couple of minutes, just let me, we'll come back and do this. So let me write down my scalar potential. At an observation point or an t will be, I integrate on dx prime, dy prime, and dz prime. And there is time also, t prime. Put the 4 pi epsilon right at the front. And we have a delta function for time, which involves finding the distance r minus r prime over c. And that is distance r minus r prime, which we will write more explicitly. Maybe in the denominator I can write it more explicitly. So this is x minus x prime square plus y minus y prime square plus z minus z prime square. That's what we always do. And then there is square root. And the charge density is q times delta function of x prime, delta function of y prime, and delta function of z prime minus vt prime. Conveniently, we have 4 integrals and 4 delta functions. So especially the space delta functions are very simple. We just have to replace x prime, y prime, and z prime with v and v times t prime. That's straightforward. But after we do that, what you will realize is that the delta function in time that remains, that's not a straightforward delta function. It contributes at more than one places, and we will have to analyze that. In fact, we will have to, it won't come out as a linear form. We will have to learn how to evaluate delta functions when the argument is not linear. We will come back and learn that and introduce that. For now, I'll stop at this point, and thank you.
Good one.
Mhm.
Thank you.
Enjoy.